Okay, so week 10. So yeah, I was just giving you a basic summary about what we have been doing and going through. Sorry, all the way to today, where we got the last two topics talking about multi-degree of freedom system, right? We're gonna be limited to 2 degree of freedom system, and basically, if you want to go to 3, 4, 5, 20 degrees, then it's all about long equations, much long equations, more math to do, but the concept is same. And as you may know that what you did with RCB, it was basically a software that would apply in part what you're going to be studying this week, because we got multi-floors, 10-story development. So the software will be just building a matrix, which today you will be able to know. And what I really want you to know is the aim of introducing this topic for you is to find out natural frequencies and mode shapes. So this first one, natural frequencies, which is happening next week. So today's kind of going to be preparation. Today we're going to be basically all about defining and establishing the equation of motion for a multi-degree of freedom system. So this is what we did, remember, all the way back to week 5. Week three. So week 3, what we did, we showed you at the very start how to establish the equation of motion for a single degree of freedom system. But today it will just be a start to go through what multi-degree of freedom means, and then we're gonna learn how to establish the equation of motion. It needs more work than what we did here. Then after that, you're going to see that we're going to do some examples. And after that, we're going to start from where we stopped and then use the equations of motions for multi-degree of freedom systems to work out natural vibrations or natural frequencies, which we all know how to convert to time periods, the Tn. And also, we're going to determine the mode shapes, which kind of help us to find the displacement of building. So that's basically the overall aim of today's topic, which also going to be continued next week. Right. So starting about multi-degree of freedom systems, they are basically whenever you're going to have more than one independent mass that is required to form up your structure, then it will be considered to be multi-degree of freedom system. So what we have covered so far from week 3 all the way to last week, we talked about one single degree of freedom system, where if you have a decent floor, that can be considered as one mass, or if you got a structure like a water tank, or any other elevated structures, that can be idealized as one mass, and you can easily ignore the supporting element like a post. So that's all one degree of freedom system. Now the multi-degree of freedom systems, and as I said before, we're going to be mostly working with up to 2 degrees. Yeah. If you want to do more than that, you're more than welcome to do so, but it's just going to be more equations to solve. But what we're going to practice, what we're going to assess you for, is up to 2 degrees of freedom systems. So you can see with this like 2-story building. 2-story building means that we have 2 decent floors. They are independently moving. What does independently means is if the ground shakes, if the ground goes left and right, each mass of those will be independently, freely moving, right? They don't need to move together. This whole floor will be moving together, yeah, because it's a piece of concrete, which have to move left or right together. But it's not dependent on this. It does not mean that the whole building have to go to the left when, like if the first floor goes to the left, it does not mean the second floor have to go to the left as well. You've got situations where the first floor will go to the left and the second floor will go to the right. We will talk about these things in the next week as well, where we want to find out the mode shapes. All right. So that's why we call them degrees of freedom. Degrees of freedom, we define this in week 3, but just saying it again. Degrees of freedom means that mass or lump mass is got freedom to go whenever it wants when the whole ground shakes or get under ground motion. So once we all agree about this definition, we got two masses that are freely moving left or right, independent of the other structural elements within the building. Then for such structure, we can go and use the skills we used many years ago when we can sketch the free body diagram, and we simply can do this for whichever floor. So what we're showing here is we can look at the second floor, cut at this level, just to have it independent from the rest, and then start applying or drawing a free body diagram. Now, what kind of forces we have there? We got the external force acting to the right, and to resist that force, we're going to have the stiffness force or elastic force pushing to the left, and also we're going to have a damping force pushing to the left as well, right? If we have damping in the system, and we had here, there was a damping in the system. Same thing for the first floor, to make it independent of the other floors. Make it independent of the other floors. We're just going to have a cut here and a cut there. And then we think about applying and finding the free body diagram. That means we're going to have, remember the difference here is we're going to have stiffness from the level above and stiffness from the level below. We got A and B. A is coming from the level above, so when we talk about stiffness, it means that we're talking about the resistance, the elastic resistance from the columns, right? We call it as a rate. We talked about these kind of things in week 3 and 4, but before we talked about single degree of freedom system, if you remember, when we had something like this, right? And we talked about all what I'm saying now. And also we had also a structure like this, like a one portal frame, which is also a single degree of freedom system because we have one level. Today we have 2 levels. So what we want to see here is how we finding the free body diagram for each floor, because where I want to take you from here is to formulating the equation of motion for such system. So for this first floor, it's a little bit complicated because this mass is kind of governed, and the equation of this mass gonna be in function of the upper columns and the lower columns. That's why we have FAS1 and FBS1, which is coming from the upper floor and the lower floor, or the columns at the upper floor and the lower floor, and that one elastic resistance. Same thing for damping. We have a damping upstairs and we have a damping downstairs, and they're going to give us both the overall damping force. So this is again the free body diagram we can consider for each floor. Now, before we go further with the modeling and finding the equation, you need to understand that there are several assumptions typically made with the theory is axial deformation is not excessive or ignored. There is, because always in buildings, we're talking about that 10-story building you design. Usually the columns get squashed a bit. They got a little bit strained. We're talking here a fraction of millimeters, really small things. So in practice, we can ignore them for buildings, more like typical residential towers and buildings. These can be ignored. But if we are designing something special, there are ways to consider them in your calculations because they're going to impact a bit the vibrations and mold shapes, right? And such detailed considerations for those displacement, like the deformation or the rotations also. There are, in addition to some compressed deformation. So there is, as I said, with heavy and heavy loads, the columns, especially at the lower levels, gonna get shortened, right? And that shortening will require us to make some adjustments to the equations and theories we're developing. Not only that, is sometimes the rotations at these corners will be significant to consider. Now, these kind of effects are not considered in the theories we go through because it's generally acceptable and adequate for residential applications and towers and buildings, but for special, like, for example, stadiums, those fancy canopies. No, sometimes because it's got those silky and cylinder sections, we have to consider those secondary effects. And such theories are, and such additions to the theory are explained to you in the textbook, but it's not something we're going to be worrying about or covering in the subject. So we're just going to neglect such effects. Right, so coming back to our single degree of freedom system, there are some notes here which we already agreed about. For example, because we consider the floor as one piece, so we can lump it or we can idealize it as a concentrated mass in the middle. And this is typically appropriate for multi-degree of freedom buildings or multi-story buildings. So going forward, same thing. There is a damping. If we have a damping in the system to consider, then it will be assumed to be linear viscous damping, which is acceptable for building as well, because we want to idealize it as with a constant and in all these formulas we studied between weeks 5 and 4 or 4 to 5. So these are just general assumptions which you need to understand in adopting for formulating the equations we're coming to. These definitions, I've already briefed you about it. So number of degree of freedoms, why we have 2, why we have 1, it is the number of masses which are freely to move in the building. If you got that 10-story building you designed, the 10-story buildings you designed, when it will undergo ground motion or a ground shake, then each floor within that building is freely to move left or right. And you just need to understand this carefully to work out. So if this is again a multi-degree of freedom system where you've got, say, 5 or 6 masses, which I'm putting for you here, right? When we say, and this is your base, if we're going to be shaking the ground here, now each mass can freely go to the left or right? There is no way where there is, yes, a case, and that's gonna also let you understand what's happening next week, because these kind of simulations will let you determine the mode shapes. Yes, we understand there is a case where the whole beam will go. Let me see if this color is ready to use. When the whole beam or the whole building will go together like this, or the whole masses will be going this way. Yes, there is a case like this, but this is what we call it the first mode shape, which is the most severe. And remember, when I asked you to look at your RCB, I asked you to look to the most severe mode shape. So, but there are other mode shapes. There are situations, I will make it in green, for example, is when maybe it will, the roof will go this way, and this one will go this way, and maybe this one stays like this. It just depends on, usually with these kinds of like this. Let me just take this away. This may be going to come here now. That's it. So the green can be another motion. I'm not saying it's the second. I'm just letting you understand there is a freedom in the motion. Now, wherever we go with more degrees of freedom, things will be more complicated, and you're going to have more mode shapes. If you got 1 degree of freedom system, you have only 1 mode shape. So 1 degree of freedom system that we done in the previous weeks, you got a system like this. It's only going to go this way or the other way. Doesn't matter. So this is, as a shape, this is 1 shape. It's going to go to the left or to the right. We call this a single degree of freedom system, which has got 1 mode shape, full stop. But when we have 2, let's talk about 2. You're going to see tomorrow we can have actually 2 degrees of freedom and 2 mode shapes. And that's what we're going to let you calculate as well. We're going to calculate the mode shapes as well as the frequencies. Okay, if you have 10 story, you're going to have up to 20. It's going to be more and more complicated because you don't know which floor you're going to go with which, and things can be. But remember, as much as you go to the higher degrees of freedom system, it's going to be more difficult to happen, like less likely to happen. They will happen, but they won't be recognizable because their frequencies are very, very high, right? And you're going to learn. Maybe I can ask you this question: which shape? Well, let me make it easier for you. Let me clean this. And I know this details we will visit it next week, but I'm just trying to think about it now, so you see how this week's topic is actually linked to next week's. And it's one thing anyway. Anyway, as I said before, your entire subject and the topics, they all link together. So here you've got 2 masses. And we're going to learn next week that it's got 2 mode shapes. One is the green, which is the whole floor goes in the whole building, actually, and both floors go to one direction. So whether to the right or to the left, it doesn't matter. But the shape is actually 1. So that's the first mode shape. The second mode shape, let me make it with red. It will be like this and like that. So here we go. Or it's not happening together, or like this. So just or like this. Can I ask you which one you think it's more? Which one is gonna be the worst? Which one will cause more impact in terms of displacing the building? Green or red? I know I scaled it in the right way, but I just want you to. Which one you think it's gonna happen with more severe response? I'm putting up a question there.
Green one.
Yes, thank you. The green one. Right, okay. Which that was how I scaled it as well with someone, but with the examples, it's not scaled. I'm going to ask you now thanks, Justin. The question now is which one you think will have higher time period or less frequency? Which one you think going to have higher time period? Like you said the green is more significant, but which mode shape will actually be happening, or which vibration will be happening with higher time period? Like it will take more time to finish a circle or a cycle. The green or the red? Next week, by the way, you're going to be calculating these things, and you're going to be finding the TN for mode shape 1 and TN for mode shape 2. Now, put it this way, the easier mode shape to happen, right? The easier mode shape to happen, it will be quite, the building will be relaxed about it. So that means the time period will be quite longer. So the time period for the green mode shape will be higher than the time period for the red shape. The red shape will take shorter time to cause or to finish the vibration out in terms of a circle or a cycle. All right. So we will look at those guys' properties. Today, what we're doing, or this week, we're trying to formulate the equation of motion that will represent this multi-degree of freedom system. That's one. But next week, I just want you to link what we're doing this week with what we're doing next week. And always the aim is we want to find out the mode shapes and find out the frequencies, because the key thing we always, as a dynamic engineers, or when we talk about vibrations and frequencies, one of the key parameters we inspect and evaluate and design with is the frequencies, time periods, as well as the mode shapes, which is to give us displacement. So the green mode shape will typically be calculated with higher time period than the second mode shape. And whenever you go more and more with the degrees of freedom, like third mode, 7 mode, 8 mode, if you have more and more floors, the time period will get reduced and the frequency is high. Okay, so we talked about degrees of freedom, and now the slides are focusing more into the parameters we have. So we just need to, I think I've already briefed you about the degree of freedom. And the free-body diagram. So for the higher rule, and the free-body diagram for the first floor. So you need to understand that U2 represents the displacement at level 2, and U1 represents a displacement at level 1. So these are, because these parameters will come in the equation, so you just need to know what they are. U2 is the displacement at the higher rule, U1 at ground, and obviously M1 is the mass at level 1, M2 is the mass at level 2, and these are external forces as applicable. Yeah, so in case there are external force, in the previous weeks we only talk about PPP, but now we have P1 and P2. P1 is on the first floor, and P2 is on the second floor. So just keep these kind of parameters in mind, so you know how we're going to use them. And I think here they are defining for you again what I've already defined. So PJ means it's either P1 and P2, and this is the elastic resistance, which is represented by Fs level 1 or level 2, and same thing for damping, Fd level 1 or level 2. So I've already briefed you about this kind of parameter, and here now we're going to come to the equation of motion, which is same as single degree of freedom system, Newton's second law. Yeah, this is something not really new for you. So what we're doing here, for each floor, we're writing our equation of motion. But at this stage, equation number 1, it's still talking about J's, and in the next page, because we have 2 floors, mathematically, to represent that, we're going to employ the topic of matrix. So that's from where the matrix is coming, because we have a system with 2 independent motions, and like level 1 is not dependent on level 2. Yes, they are in function of the columns and damping systems, which are shared. You have to understand this. So this mass is independent on the one above, but yes, it is sharing or being influenced or in function of the columns that can be shared by them. So yeah, this column is shared between level 2 and level 1. And the stiffness of these columns do have impact on this floor. Same thing, this damping will have some impact on this floor as well, as you're going to see with the equations. So based on this formula, or this one here, we're going to have 2 sets of equations. You're going to have one equation where all the j's are 1, and another equation where all j's are 2. And by math, we can rewrite it in a matrix format. So this is again just a math business to convert 2 equations where you've got shared variables, right? You've got shared variables between them. You can use a matrix system. So it's just basically a math exercise. And there's another way to represent a matrix by using the bold characters. It's not really, it doesn't matter with us because you can represent it whichever way, as you're going to see in the solutions. It's not really. So again, as I said, for today, there is kind of process. Some of the processes are very simple. It just comes from your development for the matrix itself, because we're just positioning the properties within the matrix structure. That's what we're doing. So today, as I said, it's all about how we can end up writing a correct equation of motion for particular systems. Let me show you an example while I'm talking about it. It's something like this equation. That's what really the aim of today's topic. And as I said, next week, we will start from this equation to go and work out the mode shapes and work out the time periods, which I've already started talking to you about just before, like I start bringing into the example. Okay, so let me just go back. Any questions? All right, so as I said to you, there are two ways the textbooks can represent a matrix, either by using these bold characters or by using the frames, as you see here. And in case you're going to use these characters, you just need to define each of those characters with the correct matrix arrangement, but it's not really, it does not matter for the solutions, whichever you use. So let's talk about the details. Let's talk about each matrix, how it can be developed and represented, because that's what you're going to be practicing today. Now, with the mass, you don't need to do any. We know mass. We got two floors. One is level 1, one is level 2, and if you want to establish it in a matrix, because the mass it's not in function of the stiffness, it's just a property for the floor. The mass is not in function of the column's stiffness or damping. They can sit like this. So for the first floor, yeah, this is talking about the mass of first floor, and there is no influence. So there is no influence from between, or there's no link between level 1 and level 2. They are independent, as we discussed. So basically, that's how we can establish the matrix for the masses for the two equations we have, right? Because we're going to have two equations. They are kind of no links, unlike what we have for stiffness or damping. This is damping, and this is stiffness, because it's going to be a function of the damping, which is shared kind of between level 1 and level 2. There is kind of a relationship between them, and we're going to have typically all the places within the matrix in function of stiffness or damping. We will see that next. But when you come to the point of defining this matrix for the mass, basically it's just going to be as shown here. Because as I said to you, we're typically going to work on 2 degree of freedom systems. And when you're going to multiply these matrices together, you will end up having the 2 equations we are talking about. Now, with the second property, stiffness, talking about this one now, this one, the stiffness. With the stiffness, it's a little bit more advanced, or you need to put more considerations into looking at the free body diagram we talked about. So as you can see, when I want to find the total force on the first floor, I will end up having this equation. So SF1 will be equal to the stiffness of the first floor multiplied by the displacement of the first floor. And then when I want to find the force that will be shared by the level below, here you have to subtract the displacement that was caused from the first floor. So because, overall, when the building displaced, let me clarify this here. So What we're trying to take away here, we're trying to take away the difference between the second floor displacement and the first floor displacement, because the whole building was moving. So there is no actually stiffness happening within the length H1, right? I'm talking here about the force on the first floor. So the force flow on the first floor, basically it's coming from what's happening at this floor, which is coming from multiplying the displacement one. Let's have a look. It's coming from multiplying displacement at level 1 and multiplying it by the stiffness of columns at level 1. What about what's happening with level 2? We're multiplying the stiffness of column 2 by the difference between them. We have to take away the displacement at level 1 and take away from it displacement at level 2. All right. Now, what about the stiffness which is happening on to level 2? This will be same thing. We have to subtract the displacement at level 2, take away from it displacement at level 1, and multiply it by the columns stiffness at level 2. This will give you the force at level 2. So this all comes from statics and the absolute displacement we have at that particular floor. Is there any question? And by looking to this, now we can say we have two matrices or two equations, which we're going to convert them to matrices, which we will end up converting them to matrices. And that's what we did here. So this is just copied from the previous slide. This is basically the equations we did from the previous slide. And to represent those in a matrix format, we have generated this matrix formulation. Right, so if you resolve this matrix, it will eventually give you two equations. Remember, matrix is coupling equations for us. And it's a way of representing problems where we have two different independent masses moving independently, but there are some links between them. And the links here was, as I said, K2. K2 is actually linked between the two properties here, as well as the displacement. They are kind of linked together because we have to take away one of them from each other. So these are the equations we can predict from the free body diagram, and we ended up finding the matrix format. Can you give it a look, have a look through them, and tell me if you have any questions or questions? Does it make sense? Now, one thing when you look at those equations, don't always assume that U1 is actually, because when you look to this graph here, maybe, you're going to assume U1 is always less than U2. No. As we said, this one, the way it's profiled, it is something looks like first mode shape. But as we said, there is two mode shapes. Sometimes this floor will go to the left and this floor will go to the right. So things are really variable. So I've had some questions before. Is this going to have negative impact? Yes, it can. Why not? It can have negative impact if in case it's under mode shape 1, because U1 is actually less than U2. So if we are under mode shape 1, this term here will give negative impact, and you don't know, depends on the stiffness, the displacement. we can work out. Now, we will not get really working typically with these formulas. We're gonna typically work with this one because matrices usually simplifies the calculation process, and that's why we have used matrices, just to help us to find how relationships are impacted by each other. Okay, so same thing applies to damping. So damping, same story. We do have damping number 2, which is this one. How it's calculated by applying or by looking to the free body diagram at the second floor. And the free body diagram can easily tell you FD is equal to the constant C, which we have it here. We have a damping there. So constant C multiplied by the displacement. So I'm talking first about the damping D2, which is here at the second floor. This is calculated by finding the displacement, the absolute displacement here. To find the absolute displacement here, we need to take the overall displacement and take away the sorry, you're not displacements here. Just this is not displacement. What was this? Say displacement. What was this actually? Can someone tell me?
This is velocity.
Velocity, excellent. So we're talking damping here, so I should be referring to this velocity. Yes. So we're gonna find the velocity at this floor and take away from it the velocity at the lower floor, because there is a case or a stage where both of the floors are moving together. When both floors are moving together, it's gonna give you no stiffness, it's gonna give you no damping force. That's basically why we have to do these kind of things. While we're subtracting, sometimes you velocity 2 from velocity 1 or velocity 1 from velocity, because we have a situation where the both floors are moving together because the ground is under, because it's underground displacement. So both things are moving together. When both floors are moving together, you have to take that instance away because it's not really causing any damping force. Same thing applied under the elastic stiffness. There are phases or instances where the floors are acting together or moving together, and you have to find the absolute value to take it away because it's got no influence. Now, given that we have two equations, and we're going to simplify the presentation and show it in a matrix format. Okay, these matrices are what we're going to be working with, and positioning the forces is not something you're going to be doing, because I won't ask you to be modeling different floors. We're always going to have, as I said to you from the start, maximum 2 degree of freedom systems, because it's too long to ask you to solve 4 degrees or 3 degrees. So we're going to always work with 2 degrees, and I can tell you, you will typically be using equation number 5 or equation number 4. But it's good for you to understand how this equation was developed, which is coming from these two independent equations, which were set up by basically the free body diagrams of each floor. That's basically the story behind it. In the test or the examples, we will not be doing this because it's just going to be same. We're always going to be working on 2 floors. But basically what we're going to be doing, applying these equations because it's ready for you. In an exam, as you know, you will have your note papers to work, so it's up to you if you want to write it, or if you memorize it, it's up to you. It's maybe too much for you to memorize. So, given that we've already defined our damping matrix, we have already defined our stiffness matrix, we have already defined our mass matrix, so all good. So we know now the components of our equation. Now, one thing to make a note on is the column stiffnesses. Column stiffness is something, the stiffnesses for a portal frame and all these kind of basics. We talked about it in week 3, but in case you will have a question related to such topic, we will give you this formula. I won't ask you to guess or assume, because this formula, as you know, depends on whether the bottom of the frame is pinned or fixed or roller support and all those kind of arrangements. We will give you this. The only thing you need to consider is if you have 3 columns or 2 columns, you have to multiply by 3 or 2. And you're going to see that with the examples. So up to here, we have defined the characters of all those characters or all those matrices, right? Which we know it's a 2 by 2 matrix because we are dealing with 2 degree of freedom system. Okay. Now, basically, that's what really we want to go through this week, because next week, after we develop the equations, we will end up finding the frequencies, as I said, time to. So the first example we have here is they want you to formulate the equations of motion for 2-story shear frame shown in the figure below. So basically, you have a building or 2-story building. The weight of the first floor is 2 times bigger than the first one, and this one is giving us an indication about how stiff is the floor. Now, in our questions, we will give you the formula again. We want, now this is, if you remember in week 3, we told you if you have a case where the frame is indefinitely stiffer than the other members, then you can have a special equation. We will not let you guess that equation or remember it or find it out. We will give you always, whatever the case was, we will give you whatever applicable equation to find the K stiffness. We will not give you the K matrix, we will give you the K for one particular frame. Right, so, and again, this represents, like you have here, a very stiff member, which is like a concrete slab, not lightweight floor like timber or steel floor structure. Same thing here, you've got concrete floor, but the weight of this floor is half of the first one. And you've got some properties for the upper story columns and the lower story columns. Obviously, the lower ones are stronger, they are double. You've got indication for heights, you've got external forces. So that's what you've been given, and they just want you to establish an equation of motion. All right? So the thinking process is we are utilizing equation number 6 to be used from slide 15, which is basically this general equation where I've used the bold characters. Now I scrapped the damping force because there is no damping. The question did not show you any damping, so just don't worry about it. All right, the question did not show you any damping, so don't worry about it. And then you're going to be left with the elastic stiffness and with the mass matrix. The mass matrix, you can look at your question. Level 1, it's 2m, and level 2 is just m. So remember, this number is 1, and this number is 2, so represent level 2, and this number is 1, represent level 1. So you can see with one line, we're done with the mass. And we know how to do the mass matrix, which is going to be something like this. Is constant. It's always like this. Stiffness, now the stiffness component, or this component within the equation. We know level 1, it's 2 times stiffer, and based, given that the floor is got stiffness with infinity, the failure with infinity, we can work out the column stiffness is actually calculated by this formula, but as I mentioned to you, typically we don't let students assume that. We will provide in the question, we will provide this formula to find the stiffness for one floor, but you need to work out because here we say Q is 2 times bigger. So it's going to be, because we have 2 columns, we're gonna have it as 48. And yeah, basically it's a 12, and it's already 2EA, EICIV, so it's 48, but at the second floor is only by 2. So it's originally 12 Young's modulus inertia over the height Q. That's the definition for stiffness for one of the 12, for one of the columns, like what I've proved to here. So the basic equation is this one, right? That's when the fixity is actually rigid. When the fixity is rigid. Now, if in the question you will have a pin or something like that, we're gonna give you the other formula. So we're coming here and we're finding the K1 value, which is 48 by the other factors, and K2 at level 2 here will be basically 24 times. So what we did here, we just find the stiffness for the first floor and the stiffness for the second floor. Then to construct the equation of motion in a matrix form, we then need to substitute the values as per equation 5. Equation, sorry, 4. 5 was for damping, equation 4 was for stiffness. So basically you need to use these arrangements. That's what I was saying. You're basically going to be using equation 4. So we've already determined what K1 is. We've already estimated what K2 is. You just need to apply these algebraically. You need to apply these relationships and work out your stiffness matrix. And that's basically what we did here in the solution. So you can find out, I think, yeah, that's basically how we worked out this matrix. It's coming from equation 4. And then the last step here is just putting it in the in our main equation. So you can see 70%, 60% of what we're really doing here, it's a math exercise for remembering the math process you used to use with an engineering application. And you would need to correctly figure out how the masses are distributed, or whether stiffnesses or damping and masses, as we discussed here, for the equation of motion. They will not change from question to another, because I can tell you the final exam, which I think all of you know when it's happening, when we're going to get you such question, we won't ask you for story, because you're going to need another hour to do it. It's just going to be too long to really work out the numbers. All right. So this is basically what the question is asking me to form. Now, this process basically, it is done by substituting into the pre-formulated equations here, which is equation 4 or equation 5, right? There's another way, which I will also take you through, which is by using the influence coefficients. And we may ask you to use one of them. We may ask you, because the influence can help you in special, like the very last question here. This one, it can only be solved or easily be solved by using the coefficient or the influence coefficient method. All right. So for example number 10.1 or example number 1, there is an alternative method to solve it by using the influence coefficients. Will we ask you to use one of them? Yes. Now, if we did not ask you in a final exam to use particular one, use whatever you feel comfortable with. And for this one, you don't need to write down equation number 4. Like you don't need to memorize equation number 4. You just need to know the process of doing it. Because here we look at the shapes and we keep going with the idea. And the other reason is the influence coefficient method. Sometimes it's very handy to solve a bit complicated problems, a bit more complicated problems like this frame or this question here. So let me let's have a break. Let's have maybe a break for, let's say, 10 minutes, and then have a look through it. I mean, and I will go through it. If you have any questions, come in and ask me. If you like go through the notes I've already covered, if you have any questions about them, let's talk about it now. But basically, let's have a break for 10 minutes, and then I can go through this method step by step. Then after that, I will brief you about this last example. Then you can go through it. Right, we'll leave you for 10 minutes. Then we'll see you then. What I was talking about here, it's basically formulating the equation of motion for a multi-degree of freedom system. One method is by substituting the one we applied here. We have used the pre-established equations. That was equation number 4 for the stiffness, and there's equation number 5 for the damping. Damping was not applied here because we don't have any damping system within the building. Now, with this method, what we do, we kind of, it's something similar to that virtual method, maybe if you remember using when studying structures, statics or independent structures. So what we do, we try to imagine the shape, the influence. That's what we're calling it. Influence coefficient is based on finding what shape going to happen as influenced by assumed displacement. So what I mean assumed is we're going to look at the floor. We're starting here with the first floor, right? So first step is we're going to look at the first floor, and we will assume there is 1 unit of displacement applied at the first floor, where the other floors has no displacements, 0. So in this case, we have 1 unit displacement at the first floor and 0 displacement at the second floor. That's what we're doing first. Then you just need to imagine when such action is going to be applied, how it's going to influence the frame, and you can say, you can just draw this red line which represents the influence of such displacement. Yeah. So this arrows here represent what kind of elastic forces are resulted from such influence. This arrow can be, we're not saying if it's a value or a 0 yet, but you just need to document it in any direction. Now we're always going to assume it's going to the right, and then you need to correctly label it. You need to be careful with labeling because that will help you to establish the positioning within a matrix later on. So K11 refers to having the first one. It refers to having the force applied, the displacement applied at level 1. The second one here represents where we are imposing the displacement. So again, the first number represents where we are measuring the action, and the second one is where the displacement are imposed. So if you have a look to the second floor, we are measuring the influence at level 2, while the force is actually applied at level 1. So that's basically trying to summarize it here too. So the second number typically represents where the displacement is applied, and the first number is where we are measuring the influence. So that's why the first arrow here at ground floor, at the first floor, sorry, is represented by K11, and K21 will be represented at the second floor. Then from this diagram, we can extract these two diagrams, the one at the top and the one at the bottom. So for the top one, I will draw this kind of shape, which is what I eventually got here. Draw this, right? I can represent it there. And then we can apply. Now we know at this floor we have K2 value, right? So everything for the, here we're talking about the level above. So what we're doing here, we're trying to split the influence line into two levels, level 2 and level 1. The upper figure here represents what's happening at level 2. That's all. That's why all the K's are referred as number 2. And the lower one is by K1. So at this floor, we all know we have a displacement and eventually an elastic force applied to the right. So we need to show it in the right direction. Then by statics, we need to apply statics. You can say from statics, they're going to be an opposite direction of elastic stiffness going towards the left, right? So again, these have to be carefully placed based on the influence shape. So this force or this displacement has caused this shape. Then when you come to this figure, you have to show there is a K going towards the right direction, and it will be statically balanced by another K directed to the left. So you need to show the arrows as shown here. You do same thing for the lower figure as well, where at the first floor level, we have also K1 going towards the right, and it will be opposite to a K1 going to the left to get it to static. So once you reach such two figures, you can keep this aside now. We're going to use it later. So you do these figures, keep them aside, and we're going to use them later after we finish what's happening when we're going to apply 1 unit displacement at the roof or at the second floor, and that's what we're doing here. So when the floor at level 1 is 0 and at level 2 is unit, we have to imagine what shape you're going to have there. We already agreed here is 0, so you start from 0, and here you're going to have 1 unit displacement, so eventually you will have this shape, right? That's step number 1. And as I said here, what you're going to do, you're going to put those green arrows, which represents the correct coding for the elastic stiffnesses. Here we're using 1, 2. As we said, 1, the first number represents the influence happening at that floor. The second number represents where the displacement was applied. So 2 here is at the second floor, that's why it's 2. Same thing here, K22, K11. Then we have here 1 upper floor to report in terms of elastic forces. When you put it here on the right, you will say that's the displacement we got. That's why the arrow here going to go to the right, and it needs to be resisted by another stiffness force going to the left at the bottom. Otherwise, it's going to be moving. Have to be static. Okay. So once we get to this level of graphing or drafting, you should be ready now to go and work out your stiffnesses as summarized here in this page. So now find the stiffness matrix from the influence coefficients. Before we start doing this here, you just need to know K1 for level 1 is 48 EIC. This is something from the question. As we said here, we've got for level 1, it's going to be 2 times PI. So because the stiffness here is already 2, doubled, and we've got 2 columns, and we know the formula for 1 portal frame. It is basically this. So you're going to end up with 48 Young's modulus by inertia over the height cube. And that's what we got here. That's for the first floor. For the second level, we're gonna have half. We're gonna have the first one half floor because that's given to you in the question. Now, that was just to prepare all the properties, then how to find the stiffnesses. We will just use algebraically add them together. So K11 basically, we're just going to go to the first floor here. You basically need to go to the first floor and see what's actually added to the first floor. So have a look here. You're going to be having K11 or the K11, have a look here and see where is K11. So you need to algebraically add this to that. If they are going in the same direction, so just add them plus them algebraically. K11 is represented by adding this stiffness to this stiffness, and that's basically what we did here. Now let's look at K21. Go back to this diagram, see where K21 is, which is here. And this is basically represented by negative K2. And that's why we have negative K2 here. Then K12, you go back here, K12, it's here, and at that level, we have negative K2 as well. So that's why we have negative K2 as well. Then go to the last matrix point, which is K22. Go back to your diagram you established, K22. It's represented by positive K2, and that's what we have here. So you just gonna put them all together, and then you can place them in your matrix, K11, K21, K12, K22. And your matrix should be same as what we had. We should come back to this values as well. So that's basically just showing you how we use the influence coefficients to work out or formulate the matrix. Is there any question? It's just two methods. Yes, we may ask you to use one of them. One of them, which is the second one, this one, you just need to know the process and you don't need to memorize or write any formula. Like some, this formulas, you may wish to write it on your note paper for the exam, for the final exam, but if you prefer to solve through these diagrams, it's up to you. Sometimes we may ask you to use one of them, so you just need to learn both of them. And all what we're doing today is just to write down the equation of motion. Next week, we will, as I said, start from here to work out the mode shapes and to work out the frequencies or time periods, whichever. We have a very last question here. Look at and what we have here. Is there any question about what we did so far? Right, so can someone explain? Let me brief you about this, and then this is, yeah, I know it's a textbook image, but it can happen in various applications. So what we have here, it is different than a building. This is not a building like elevated building and you've got a ground motion to shake it. This is basically just maybe a steel beam, and you do have some stiffness or flexibility at both ends. You got 0.1 and you got 0.2. So there is some sort of stiffness or softening, right? And there is a mass, a uniformly distributed mass for that beam or structure, or maybe it's, you know, we talked about some air conditioning unit or chillers. They're not like those small air conditioning you use for your apartment or room, like a very large, maybe 3 meters by 5 meters chillers. They are air conditioning units for hospitals or for building, quite heavy. these they are typically fixed to steel beams that will be fixed on top of the roof beams for your building. So basically, this spring, can be representing another beam. So there is another beam like this. Or maybe I can draw it here. So there is maybe another beam, like a roof beam. Make it here even. Maybe there is a portal frame here and a portal frame there. Right? That's just a roof beam. This is the roof beam, beam, and this is a roof beam. And this is just a column. And usually we are able to estimate a stiffness as a spring for this roof beam because it will be acting as spring. Same thing here, and we need to support the units. They're going to be maybe a couple of beams, and all those beams and the chillers on top, they are basically that unit I was talking about, which we need to we need to study its dynamic influence. So the question now is just asking you at this stage to basically find the equation of motion, which was what we studied this week. And those chillers, or those units that I was talking about, they, yes, typically impose some rotational action into the system. So it's very, very applicable to have such loading arrangement. All right, so we've been told there is a rotational action or a rotational force that can be applied into the mass, and there is also a vertical force that can be applied to the center of the mass. So that was all given to you. And again, you formulate the equation of motion with respect to displacement u1 and u2 at the ends. So in function of u1 and u2. Now, this one basically, it's just because it's a practical example, that's why I put it for you in the notes, which someone may end up reviewing. But there are some skills which are kind of basic skills that you studied at engineering, like this virtual method, and I've kind of helped you as a reminder with it. So there are some basics which I'm not assuming all of you will remember, but for things which are a bit not straightforward, I have part of the solution. They basically try to work like the first step. What we're doing here is we try to find the applied forces, the applied equivalent forces on that mass or bar, which is this one, right? That's the first step they're doing. And to do this, they have used the virtual displacement theory, which I'm assuming you may be able to remember. If not, I've tried to work out some details here. So based on the actions applied on the mass, we have the linear forces, which is coming from here. And that's basically average. So what they did, they find the displacement at the end, and then to find the average, virtual the work done by the applied forces, that's what we calculate. So we try to find the work done by the applied forces. The applied forces, we got the linear force and we got the rotational force. For the linear force is easy. Because here we got maximum displacement, here we got zero displacement for one of the cases we have. And what we do to average it, we take half. That's why we divided it over 2. Then we multiply the displacement by force. Multiplying displacement by force will give you the work. And then what we did here, we're finding the work generated by the rotational force, which is also in the center. How we worked it out is, again, by static. We just use taking the moment around one of the points will work out, giving you this relationship here. In case some student didn't know how this was worked out, I've just showed you how this is done. right? So whatever we did here, whatever we did here, we're gonna apply it for both points, yeah, because we assuming down the influence line, we're using the influence line, by the way. What we did here, we have used the influence line method, which took you through here. We're using same concept of the influence. Otherwise, it's easier to apply this method. So the influence lines, they actually established, it is like shown here, they saying 0 on one end and 1 unit on the other end. And from here, they're going to work out the forces and reactions at the ends. And that's basically what they did. So they did it on, they did it at the left side, they did it at the right side, and they end up finding P1 and P2 same methods. Okay, so this is usually the forces that was determined at the ends. Then by determining the forces, we're going to go and determine the matrices, which again would follow the concept of influence lines. So they use the influence coefficients. I don't want to delete this. I think I can delete it now because you have those files uploaded. So basically what we did here, we have used, so if I delete it, I'm going to take away all the relate it one by one. So what I'm trying to explain to you is we're using the influence lines. You have to be on top. So maybe some of you still not 100% maybe followed me in terms of this process, but I suggest you to I suggest you to solve this without looking. So yeah, go through it with me, go through it. Then if you're comfortable with it, close the notes, try to solve it without. Then once you understand it, you can apply same thing here. They kind of follow the same thing. They will assume one end got a unit of displacement, like here, for example, U1 is displaced by 1 unit, while the other ends are all 0. And they're going to work out the influence from such action. So eventually you're going to end up finding the stiffness for that beam, horizontal beam. And same thing, we're going to, with the same concept, we're going to determine the mass. But with the mass, you just need to go and use some statics. I did help you with the formulation here, right? Because with the mass, when we have a unity on one side, you're going to have this triangular shape. And to find the equivalent inertia from this equivalent shape, we have to apply statics and find the equivalent. It's not difficult. It is just the process may be new for you. So the skills, I'm sure you have them, because some students will come and ask me from where we actually find this one. Why we're not using the full mass? Why we're using 1/3 of the mass? We're using 1/3 of the mass because when we are applying load here in the rotation, we're not carrying the entire steel beam. This point is only carrying part of the steel beam or the unit, whatever it is. So to find it out, we have to apply the influence line, and then our equivalent force will be 1/3 from the maximum or 2/3 from 0. Then apply statics to find A or B. And that's how I found FA is 1/3 and FB is 1/6. Right? These are frequent questions. I know a group of students will do it from this week. I know a group of students will not do this and wait until few hours from the exam, and they will come and ask me few hours, like one day from the exam, maybe 10 p.m. They come and ask me, how did we find this? How did we find that? They are basics. They are not something. They are not coming from a new kind of methodologies. They just statics. Basically, we're applying statics because we need to know the percentage of mass that will be carried by whichever end, depending on the influence line we are modeling, right? So all those hidden all those hidden difficulties, I don't want you to spend much time on it. I've written it for you here. So carefully go through it, but I don't suggest you to go through this example before solving this by your own without looking at the steps. So solve this without looking to the step, then go through these concepts and these ideas, and eventually you will end up finding our equation of motion applicable for that roof beam system that would carry a unit like those chiller units and those dynamic units on top of floor. Same thing applies if you have a generator, for example, like a mechanical generator sitting on a suspended slab, and you need to check its dynamic properties. Remember, today we only have developed manually, not by computer. We wanted to develop an equation of motion. Next week, we can do more steps to find the time period and the frequency, which is the key thing we need to. Now, this is very, very practical application, as I said, because when people look at this, they will think it's a 1 degree of freedom system. No, it's not, because we have 2 quantum frames of springs that will make it double degree or 2 degree of freedom. And there's a lot of applications. For example, if you've got a generator or an MRI unit in a hospital sitting on a special slab, the key thing they're going to ask dynamic engineers to check is it safe? Can the slab take the vibration without a problem? And that's what we're doing. We all know we have to go and find the natural frequency. And but once you find it, you can then assess it and find out whether it's close to the forcing frequency of the equipment or not, and give a decision, make a decision. So go through these 3 examples before we meet next week, and I believe you will be on top of that topic, and I can guarantee you will have one question in your final exam related to these 2 last topics. So just make sure you learn it on time. It will be running easily for you. Any question?